In this video I'm going to talk about deriving Runge-Kutta methods using rooted trees. Okay, so the derivation of a Runge-Kutta method is essentially achieved by comparing the Taylor series expansion of the first order ODE, so this is the ODE we want to solve, and comparing the Taylor series expansion of this to the Taylor series expansion of a general form of the Runge-Kutta method. And what we then do is we want the two expansions to match, so that gives us some order conditions, and these order conditions place a series of constraints on the values of A, B and C, and these order conditions need to be satisfied to produce a Runge-Kutta method. Okay, so we're going to start with looking at the series expansion of the ODE. So this is the well-known Taylor series. You should all be fairly familiar with this by now. What we're going to do is we're going to use it to solve a first order autonomous ODE. Now I just mentioned autonomous ODEs is where we can write the ODE without the variable t. Now the reason this is done here is purely simply to simplify the derivation. It doesn't have any effect on the validity of what we're doing here. It's just a way to make the derivation a bit easier. Okay, so if we're going to solve this one, with the Taylor series we need higher order derivatives of y. So we've got the first order derivative, so y dash is equal to f of y. So to get y double dash we need to differentiate f of y. Now of course f of y is a function of a function, so remember y is a function. Okay, so using the chain rule, okay, so we derivative of f of y multiplied by the derivative of y. But we know that the derivative of y is itself f of y, so this gives us our second order derivative y double dash. Okay, to find y triple dash we need to differentiate y double dash. Now here we have functions and functions, and we also have these product of these functions and functions, so we need to use the product rule and the chain rule. Okay, so in doing so we get this. We can see we have a couple of y dashes, so like we did before, y dash equals f of y, and we get this expression here. So if we were to continue, if we were to calculate the fourth order derivative, okay, so we'd have a couple of applications of the product rule here with the chain rule, and also here. So we're starting to get quite complicated. The whole process is starting to get quite complicated. Now this is where trees come in. So to avoid this complicated approach, John Butcher, who the Butcher tableau is named after, made a really useful, interesting observation that the higher order derivatives for our first order ODE match that of the set of rooted trees of that order. So for example, we've looked at derivatives up to order 3. So what we're going to say is introducing some notations. So the bold type f is simply f of y. So bold type f dash is f dash of y. Okay, so these are the first 3 derivatives, so derivatives up to third order. Okay, and what I'm going to do now is on the next slide you'll see how this matches that of the rooted trees up to third order. Okay, so what we had is y dash was equal to f. And what we're going to say is let's say f is a rooted tree containing one node. The second order derivative was f dash f, and what we're going to say here is a dash after the f denotes a node with one child. So if we were to represent this in rooted tree notation, or as a rooted tree, we'd have f dash on the bottom with one child containing f. Now for the third order derivative it comes in 2 parts. Okay, so the first part is f double dash ff. So what we have here is f double dash, so this denotes that this rooted vertex root here has 2 children. And the second part was f dash f dash f. So we have on the bottom our root node is f dash, that has one child. That child also has f dash also has one child, f. So what we have here is these are the 4 for rooted trees up to and including order 3. There's no other rooted trees in that set. Okay, so you can see how a set of rooted trees actually corresponds with the derivatives in the Taylor series expansion. So this is a really, really useful and quite significant and, to be honest, amazing observation, and it makes things much, much easier. Okay, to actually make use of this in the Taylor series, what we do is we define what we call elementary differentials. So essentially what we have is capital F. Okay, this is going to be linked to our lowercase f. So capital F of tau is going to be equivalent to the derivative of y. And for all other trees, our capital F of a rooted tree is going to be equivalent to the nth order derivative of y. So this is some rooted tree here. Okay, and we'll have a series of trees depending on what n is, depending on how many trees we have. So for example, you saw in the third order derivative, if I just go back that one, back up a couple, we see we have 2 separate rooted trees. Okay, so in that case we had T1 and T2. So this allows us to write the Taylor series expansion of the first order ODE like so. So here we have, this is our y, okay, and then we have the summation. Now this summation is over the set of T is a member of, little t is a member of the set big T, and the set big T is a set of all rooted trees up to including that order. So, and big F of t is the elementary differential defined up here. Okay, so you see we have some coefficient of big F of t. So h is our step length. Okay, RT as before is the order of the rooted tree T. Sigma is the symmetry of the rooted tree T, and gamma is the density of the rooted tree T. Okay, so what this is this is a Taylor series expansion. So what we also need to do now is do the same for a Runge-Kutta method and match it to this. So if we do the same for Runge-Kutta method, this is what we have. I've skipped over some of the detail here. If you want to look at the detail, check out the lecture notes, or also some textbooks which are referenced in the lecture notes. Okay, so the series expansion of the Runge-Kutta method using rooted trees is this. Okay, so we've got the same y as we had before. We have the same summation over the set of rooted trees. H to the power of the order of the tree T. This time it's just divided by the symmetry of T. Okay, we can see before we had it over the symmetry times the density. But the difference here is we have this phi T. Okay, this phi T term here, this is known as an elementary weight, and each rooted tree has an elementary weight which is it's a function of A, B and C coefficients from a Runge-Kutta method. Okay, so if we what I've done here is I've copied in the Taylor series expansion of the ODE. This up here is a Taylor series expansion of Runge-Kutta method, and you can see they're very similar. Okay, so if we equate these two, we can see that this phi of t, if this is equal to 1 over gamma t, these two are equivalent. Okay, so what this means is we know what t is, because let's say we're going to derive a second order Runge-Kutta method. So we have the set of all rooted trees up to including order 2. We know what their density is. Okay, so each tree we have 1 over the density, and for each tree we also have an elementary weight. So how do we determine this elementary weight? Okay, and it's determined using this sort of process here. So if you've got a tree, for each non-leaf vertex, okay, so that's any vertex which has a parent, or any sort of edge which has a parent and child, we associate a label I, j, k, etc. Where we attach I to the root vertex, and we write down a sequence of factors. So the first one is always going to be bi, because that's the root vertex. And for each edge of the tree that does not terminate in a leaf vertex, i.e. each edge which connects a parent to a child node, we write down another factor A, and the subscripts of A will be the parent subscript and the child subscript. So in other words, where an edge joins vertex I to vertex J. And for each leaf vertex, we write down a factor which is C, where CJ, where J is a subscript, J is a label attached to its parent vertex. Okay, so B, the elementary weights always start with BI. Then we have, or we may have some A values, depending on what your tree looks like. And we'll have C values, which are for the leaf nodes. And then what we do is we sum the product over all possible choices for the labels. Okay, so let's have a look at an example. So here we have a tree. I've written it in tree notation here. So we've got a rooted tree. So this rooted tree consists of two subtrees. One subtree has a parent node and two child nodes. The other subtree has a parent and a child node. Okay, so we can sketch this out. Right, so the first thing we do is we associate I, the label I, with the root node. And for all other nodes which do not terminate in a leaf node, i.e. here we have, we don't label these leaf nodes up here, but we label these J and K as well. By the way, it doesn't matter which sort of order you label these in. Then what we do is we form our elementary weight. So we always start with BI, because that's for the root node. Any edge which does not terminate in a leaf node is our A values. So here, this edge here starts at node I, terminates at node J, so this is AIJ. And this edge here starts at I, terminates at K, so this is AIK. J has two child nodes, so these two leaf nodes here, we're going to label these CJ and CJ. You can see we've got two nodes there, two values CJ and CJ, and this leaf node up here, its parent node is K, so we label that CK. So here we have a series B's, A's and C's, okay, and we sum those over all possible values by JK. Notice here that obviously CJ times CJ, we can write that as CJ squared. Okay, so to derive an explicit Runge-Kutta method using trees is actually very, very simple. So per pth order method, we need to satisfy this condition for all trees in T, which is a set of all rooted trees up to with an order up to and including P. Okay, so if you have 4 trees in T, we'll have 4 conditions to satisfy. That is in addition to what we call a row sum condition, which means our value of C has got to be equal to the sum of the equivalent row A. So Ci is the same, or needs to be equal to the sum of the values of A from row I. Also, we need for explicit Runge-Kutta method, C1 is always 0, so that means A11 is always 0, and matrix A is lower triangular, so Aij will be equal to 0 whenever I is less than or equal to J. So let's have a look at an example. We're going to define a second order explicit Runge-Kutta method using trees. So first thing we do is we list all the rooted trees with order 2 or less, which is quite a simple thing to do. It's just 2 of them, just the basic tree with order 1, and there's only 1 tree of order 2. Okay, so this gives us our 2 trees. A second order explicit Runge-Kutta method had 2 stages. Okay, so the elementary weight, so we're going to sum, we've only got BI's here. Okay, so the sum from I equals 1 to 2 of BI is just B1 plus B2. And for the second tree, if I label this node I don't label this node because it's a leaf node. So we have BI, but we have a leaf node, so that's going to be CI. Okay, so BI there and CI. So if we sum those over I equals 1 to 2, we have B1 times C1 plus b2 times c2. Another thing we could take into account is that c1 is always 0, so this, when we look at the order conditions, that term is going to disappear. Okay, so just go up a bit. Now the density of this tree is 1, so therefore b1 plus b2 is equal to 1. The density of the second tree is 2. So remember, to calculate density, we assign a label of 1 to the leaf node and a label to the parent node of 1 plus 1, which is 2, and multiply them together. Okay, so that gives us 1 over 2. So here we have our order conditions, and that's from the set of rooted trees. Now, as I mentioned earlier, since C1 is equal to 0, and if we include the row sum condition, what we have is we have a system of 3 equations and 4 unknowns. So we have b1 plus b2 equals 1, we have b2 times c2 is equal to 1/2, and we also have the row sum condition, a21 has got to be equal to c2. So we've got b1, b2, c2 and a21, so we have 4 unknowns in 3 equations. So if we set one of these unknowns to be a value, we can solve for the other 3. So for example, if we choose c2 to be 1, and this results in b1 and b2 are equal to 1/2, and a21 by the row sum condition has to be equal to 1 as well. And this gives us this Runge-Kutta method, which happens to be the same as the classical second order explicit Runge-Kutta method.